To our second talk of the session. It's my pleasure to introduce Matthias Degroote, who's going to tell us about coupled quantum classical dynamics in the Liouvillian framework. So yeah, take it away. Thank you.
Thank you, Bill. Thank you, Brigitte, for inviting me to this conference. I've seen many interesting talks so far. So what I'm going to talk to you about today is linked to what Ivan talked about this morning, dynamics of electrons, and I will take a different angle than what Ivan did. So Ivan did a lot of work to simulate everything together, nuclei and electrons, and what I'll do is try to stick to the Born-Oppenheimer approximation and simulate the nuclei classically and the electrons quantumly. So So I'm working at Boehringer Ingelheim, which is a large pharmaceutical company out of Germany. So you might think, why does Boehringer Ingelheim have a quantum lab? So quantum computing is supposed to give new insights into simulation of quantum systems, and we hope that by leveraging this technology, we can get more accurate predictions and basically improve our decision making, which then would speed up the development of drugs. So that's basically the angle that we take. It's a bit of a risky position, since the field is quite nascent, and especially the applications. But that's where we come in, and we try to sort of bridge the two worlds of the theoretical and the very abstract into a more applied science that's on our company side. So where do we think that the applications lie in the pharmaceutical sector? Well, that's mostly in these early areas of the drug discovery cycle, where we perform a lot of computations on our molecules. Most of our drugs are small molecule entities, so we try to inhibit or encourage proteins function by binding with small molecules. And what we need there is a lot of simulations to extract, for instance, which molecule binds best to the protein, whether or not you bind to unwanted proteins, so you become toxic, how long a drug stays in the body, and how long it takes to get rid of it. So that all comes into the decision making during the drug discovery cycle, and getting better data there definitely helps us progress faster. So we get asked a lot as an industry partner, like what are your problems and what is it that you care for? And we actually wrote this perspective in Nature Physics. And I must say that's about 3 years ago, where we put forward quite a lot of interesting avenues and areas where the field could help or progress. And I think that either by our work or just the general field's work, many of the open questions have been addressed, or sort of at least some progress has been made. So that makes me quite optimistic about the state of the field and where it's heading. So today I'll be talking about these two, and what's basically the common factor there is that you want dynamical properties. So you want properties of many different configurations of your molecule and your protein. You want properties at finite temperatures in the body. You want solvation. So you need a lot of ensembles of geometry. So you don't want to calculate the energy of a single Hamiltonian. You want to evolve the system over time and sort of get ensemble averages over your energy. And that's what I'll be talking about. So what drives this internally is molecular dynamics. So it's used for free energy calculations. So basically, the free energy determines the rate of reaction. So if you consider binding, the free energy difference determines whether one drug is a better binder or the other one, and then that's captured by this free energy difference. You can use molecular dynamics as a microscope, so you basically watch what nature does over time, right? Like a drug approaches a protein, where does it bind, how does it bind, that sort of stuff. And then it's also the natural avenue to find equilibrium geometries, to find which geometry is most favored in energy. And that's not only an electronic thing, you really have to move the nuclei. So that's how it's done classically. You take your nuclei, they have a certain position and momentum, and then you solve basically Newton's equation with the force. And the force has a classical component through the electrostatic interaction of the nuclei. And then at the same time, there's a contribution from the electronic wave function and the electronic energy, which pulls or pushes the nuclei in a certain direction. And of course, how large your time step is tells you how small of a resolution you have. If you want to look at microscopic interactions happening, you need basically picosecond sort of resolution, and you need to run this for quite a long time. So that's microseconds is basically what you're aiming for to see biologically relevant things happening, or even to equilibrate your system, right? To go to an equilibrium distribution. So that takes quite a lot of time, and these 10 to the 6 steps, that's sort of a killer, and it really limits the size of the things we can simulate. And there's lots of efforts by for instance, Schrödinger and Dow Chemical to push this up and to like do longer simulations. We've tried to just do this molecular dynamics and translate it into a quantum algorithm where we purely calculate the force on the quantum computer. So we keep the nuclei on the classical computer, but each time you want to move the nuclei, you need this property here, and that's the one you calculate on a quantum computer. We did that with the team at Google Quantum AI. And in fault tolerance, we came up with 2 algorithms. We also did NISQ, but I'll talk about the fault tolerant part. And this will come back in a later part of the slides as well. So either you do numerical finite differences, right? Like you move your nuclei forward, you calculate an energy, you move the nuclei backward, you subtract, and you divide by the separation, and that gives you your force. You can do, this is just a second order finite difference, but you can do higher order formulas as well. And this is like a loop over many calculations of an energy. And you need to do this for each of your nuclei. So if you have many nuclei, this gives you like a number of nuclei scaling in everything, right? And there's another approach, and that's this one, where you take the derivative of the Hamiltonian, and instead of calculating differences of energies, which can be quite noisy, you now calculate an expectation value of this operator. This gives you a whole new set of problems, because quantum computers are quite good at finding eigenvalues of things, but finding expectation values is not that easy. In the first place, you already need to find the eigenstate you look for, and then you also need to find the expectation value of this operator. We spend quite a lot of work also with PsiQuantum to then optimize this algorithm and do full constant factor quantum resource estimates on that. And if you look at this one, maybe it's a bit small, but for quite small molecules that are not of the order or of the size that we need. You are looking at something between 10 to the 16 to 10 to the 22 Toffoli gates. So that's for one evaluation. So there you're sort of out of your depth. You're probably not going to do 10 to the 6 loops over this. So what did we try then? So we then tried to avoid this evaluation of these forces, right? Like in molecular dynamics, there's nothing that tells you that you need to know these forces. They are not functional. What you're really interested in is the trajectory over time and eventually the Boltzmann weights and the free energy, for instance. So you're looking for the ensemble properties. You're not per se looking for these forces. So in this work with the University of Toronto, we tried to avoid calculating forces by doing everything coherently on the quantum computer. So how do we do this? So if you look at what you normally do, so you have these equation of motions for your nuclei, and you now, instead of doing this classically, you want to do this on the quantum computer. There's quite a few problems. So these equations are nonlinear and non-unitary. So either you do these things to linearize these, like Karaman linearization, or you do some Schrödingerization of this thing, or we chose for another approach, and that is to do Lagrange-Hamilton dynamics and write this evolution of the density as Liouvillian evolution. So to do that, you need to write, instead of only taking into account positions, you now have to have a density over the whole phase space, so positions and momenta. And then this Liouvillian here determines the dynamics of this system. And this already looks quite a lot like a Schrödinger equation. There's another trick that we try to leverage here, because this rho is a density, but it's a classical density, so it doesn't have any negative off-diagonal elements. So you can make the Koopman von Neumann trick, and you can go to basically the square root of this density. And this looks now fully like the evolution of a wave function under a Hamiltonian, and that's then the thing that we will simulate. So a bit of a sidetrack about the ensemble. So if you do this purely with this nuclear Hamiltonian, where you have the classical part, where you just have electrostatics, and then the electronic part, which is basically the ground state energy of this approach, of this Hamiltonian, sorry, then you arrive at some microcanonical ensemble, which would not give you very interesting dynamics, right? So what we actually want is, in nature, is either finite constant temperature or constant volume calculations. For things in the body where you have a lot of water, these ensembles are basically similar. And the way people normally achieve this in MD calculations is by including thermostats. And the most used thermostats are sadly not Hamiltonian, so you cannot use them in this Lagrange-Hamilton dynamics. But there is one that's quite old, but still works, and that's the Nosé thermostat, which basically introduces a new variable S that evolves like the position of a fictitious Bath variable, and that also has a canonical momentum. And then you have some extra terms in your Hamiltonian, and you need to rescale your momentum by S. So you do dilate the momentum, basically. But you can simulate this as a closed system, and then later trace out this S and this momentum, this canonical momentum of the Bath variable. And that that gives you your Boltzmann-weighted NVE ensemble. So that's basically what we want. So this trick allows us to do like a closed system evolution while in the sense of just the nuclear variables, it's an open system that's connected through this path variable. For the encoding, we need a phase space encoding, and we do this by a grid sort of decomposition of your positions and your momenta. So you can see an example here. So if you're normally would track the position of your nuclei and the momenta, you now import them into a phase space, and the amplitude of these vectors are basically the square roots of your density. And then, this is an example of what it would look like to have a peak distribution. This would mean that you have a Gaussian uncertainty on your position and on your momenta. So in the evolution, we split the Liouvillian into a classical part and a quantum and an electronic part. The classical part just takes the classical dynamics of the nuclei into account, and that's fairly straightforward. So all of these operators are basically diagonal. So this is a two-body operator. This is one body operator in momentum. And they are basically diagonal, and you need also to account for the differentials, and these we implement by, again, finite difference formula. And you just carefully implement this block encoding, this block encoding, this block encoding, and this block encoding, and then you combine them again. So it's basically a lot of LCUs in LCUs. And then once you have the block encoding of this thing on top, you do a Jacobi-Younger expansion, and you calculate the exponential of this operator, and you multiply it by the time you want to evolve. So you don't need to actually time slice it. You can just evolve this all the way through. For the electrons, it's a bit more complicated. So what we actually do for the Hamiltonian is we do a block encoding of this electronic Hamiltonian. It's the first quantized plane wave expansion of the electronic Hamiltonian. The reason why we do that is because this one only depends on the positions of the nuclei into the electron nuclear attraction, and none of these parts depend on the momentum or the position of the nuclei. And then when you calculate the ground state of this, it can be done controlled on the position of these nuclei. So you can calculate all of the nuclear positions, electronic states, without having to load different Hamiltonians for it, which is quite easy. So only the arithmetic of calculating this part is controlled on the nuclear positions. So it's quite efficient to do it this way. For each of the nuclear positions, though, you need an oracle that calculates or provides you a good initial guess for the electrons. This is sort of a problematic statement, because if you put a square box around your nuclei in the phase space, it might be that some parts of this square box have a really, really exotic electronic structure because you're so far away from equilibrium. But one of the things that saves us, and that is maybe underappreciated, is that in what happens here, only things that have amplitude that's different from zero really need to be accurate. So if we don't go to a region in phase space, our initial state preparation doesn't kill us so much. So we will scale with the overlap between this state that we can prepare here and the real electronic ground state, but it's only for points that have non-zero amplitude. Of course, you don't know ahead of time where in the box you will go, but you can assume that it's not like in the extreme corners of it. Yeah, so this is now for the ground state energy. Of course, you need to not have the ground state energy, you need the derivative of the energy. And we implement this derivative of the energy through finite difference again. So this is the first approach that we also developed with Google. We do only first order here, no higher order formula, because it would be too complicated. And then you need to combine this electronically, you evolve forward, you evolve backward, and you can actually implement the exponential in sequence, like these all commute. So you can make a product of these terms, and you can do that by diagonalizing this momentum operator and then just doing a single forward and backward shift with this operator. So this is how you get one term, and then you can get the exponential through controlled Hamiltonian simulation. So this thing is done. So yeah, this would be only to get to the d, but then you get this exponential of d through controlled Hamiltonian simulation. Now you have e to the I L classical and e to the I L electron, so you now need to combine them. And what we do there is split this time into smaller intervals and do a higher order Trotter expansion to sort of lower the error as best as we can. So the evolution scales in this way, where n is the number of nuclei, mu is the one norm of I think it's the maximum of the one norm of L classical and L electron, and we scale almost linear in time and linear with this one norm. This delta is actually I think it's the overlap with the ground state, and gamma is, delta is the gap of this electronic Hamiltonian, and gamma is actually the overlap between the ground state, like the minimal overlap between the initial state prep and the true ground state. So the extra Toffoli's actually scales a bit worse with the number with respect to the one norm of this Liouvillian operator. Yeah, this might clarify it a bit more. So you do the nuclear Liouvillian evolution, the electronic Liouvillian evolution, and then you loop around this for the Trotter steps in the Trotter formula, and then each one of those is split in their own evolution. So where here you have the ground state preparation, and then the forward and the backward, and here you just have the plain evolution over the block encodings. So this now gives us evolution over these Liouvillians. That's not enough. What we're actually after is the calculation of the absolute free energy, and that can be done so by looping twice over this Liouvillian time evolution. So once to calculate the internal energy, which is basically just getting an expectation value of your classical nuclear Hamiltonian. And then the entropic contribution is a bit more difficult. And you can see that you can actually get this by calculating the von Neumann entropy of this system density, which is basically the trace over the path, over this S and PS of your evolved state. Calculations of von Neumann entropies are NP hard in the worst case, and that's also here seen here. This eta is actually your number of grid points to the 3n. So this scales very bad in the number of nuclei, and we searched for really hard to get around this, but we were not able to do that for the absolute free energy. You can do some coarse graining on the grid points, but that's just a patch. Eventually, you scale with however many coarse grained points you have, but you might need a certain resolution in the evolution, and then not in the calculation of the Boltzmann weighted ensemble. So that's why coarse graining might be better anyway. So this was actually the first time that someone made a coupled classical quantum algorithm for MD. So I know Ivan likes to do the non-adiabatic, but we are very happy with the adiabatic, since most of our molecules are really on the ground state potential energy surface. Ensemble properties is something that was very elusive before, but we are very happy to be able to calculate those. There's also bad points. So grid-based approaches, there's a reason why nobody executes these. These are very costly, and it's also very hard to actually get an idea of what they cost, because this is sort of the number of parameters you need to estimate to just be able to tell you what the number of gates would be. And for any system, these are like the equilibration time, even the error you need. It's really hard to estimate. So it's not easy to actually get a decent resource estimate, even though we do agree also that it would be outlandish large, right? This is not a cheap algorithm. You basically loop over molecular or electronic ground state search, so cannot be cheap. One question that stayed very relevant is, can we do this free energy calculation more efficient? And we actually got contacted by the people from Quantum Motion and Oxford, George Huang and Balint Koskor, and they were telling us this trick with the finite differences and doing a Trotter formula. This is plain silly. You should do only block encodings and combine block encodings, and that's what we did here. So there's also a slight spin. So in the previous algorithm, we calculated the absolute free energies, and in this algorithm, we will calculate something that's slightly easier, and that's the relative free energy. So the free energy is a state function, so it doesn't care for how you got to this state. And if your molecules are very similar, or they share some geometry features, you can actually interpolate between two geometries. That's why it's called alchemical integration, right? Alchemical free energy calculation. And we actually can choose a path that's linear, and then you just need to interpolate between Liouvillians between your two systems, and that's what you see here. So this is like the red to the blue goes through two more points that are pink and purple, and that just means that you need to control the evolution of the red, pink, purple, and blue Liouvillians, and then take the difference of the two Hamiltonians between the blue and the red with respect to this ensemble. There were quite some new elements in this algorithm, why it's better. So we did actually use QSVT, but we took the other way to calculate forces, and that's with the force operator. So instead of doing finite differences, we now use block encodings, and by measuring our qubits and undoing the ground state calculation, we actually get the energy derivative through the force operator. And the rest of this circuit is the same, except for, since this is a block encoding, we can now just use linear combinations of block encodings all the way through, so no trotterization needed, and that saves us a lot of resources. We also don't have to, this algorithm doesn't need any von Neumann entropies. You just need internal energies, so that's also one costly step that's excluded, so we don't need to calculate any entropies. And eventually, this free energy is calculated by a Hadamard test to get this final value, and that's where we get a 1/epsilon scaling. And you can see here, there's no eta scaling in here, so this doesn't scale with exponentially with the number of nuclei, so that's good. And also the scaling of the Liouvillian simulation is exponentially better with respect to the error. So that's also, some polynomial gains through using the force operator instead of the finite differences. So this free energy calculation problem is now solved, even though it is a different task. Like the relative free energy is a bit easier than absolute free energies, but that's also an issue in classical quantum chemistry. There were some new things reintroduced. So, for instance, the thermalization time. We evolve all Liouvillians that we use in our path over the same time, and that's sort of suboptimal, we think. You might want to introduce a variable time for different Liouvillians. And then, there's a sense in which you share parts of the Hamiltonian between similar molecules, and we don't make a use of that, but that's very system dependent how much that would save you. And there's another issue that the referees also brought up, is that we say that we take into account like 1/epsilon scaling, but it might be that there's some dependence between the equilibration time and the error that you actually simulate, the constant error for the free energy calculation. So longer evolution might give you a better error. So it might not be fully independent. All right. So for us, it's fairly clear that the classical algorithm, translating the classical algorithm onto a quantum algorithm and just using it as a black box to get forces is kind of flawed. We try to give a good coherent counter algorithm. And we think that there's many improvements possible. So for instance, all of these block encodings, they are all locally optimal, but you combine things, you might do the whole thing at once, and that might be more optimal. And then we think that just looking at the experience that we have here, like absolute free energies, exponentially hard, and then the relative free energies being polynomial, we think it might be worth to scan more and more different algorithms and switch the primitive a bit so that we can find more tools in the toolbox, and that the conclusions might, for one type of algorithm, might not hold for all the rest. So there's still lots of work to do. That's it.
Great. Well, let's all thank the speaker. And if we could take questions to the coffee break and to the panel, that would be great. Thank you so much.